Hey class, it's Bill back with another video on linked lists. In the first video, we introduced the concept. We talked about the idea of how things are different from an array, how linked lists are going to be different in terms of their memory usage and various things like that. We talked about hazard relationships and the fact that an item of one particular type can certainly point to another one of the same type in memory using a reference. There's nothing wrong with that. In fact, that's how we're going to build these things. So we looked at the idea of nodes, how those work and how we can navigate them in a very basic way. Now what we need to do is start talking about what are the concepts that we want to keep in mind, what are the precepts when we're talking about coding, and then we're going to look at the algorithms and code themselves behind on a linked list. So here's what we want to do. Okay, so there's two different ways to talk about size. If somebody says, hey, how many items have I got? That's a very typical thing. I've asked you to hold on to my items. How many of them are there? Well, one way to do it is that you walk down the list, you traverse it, and you go and count the nodes. And then you tell them how many. Or, of course, you can maintain a size instance variable. The latter seems a lot more efficient as long as you have track of when you're adding and removing things, which of course you have access to. So I would do the second, but certainly as a mental exercise, it is not a bad thing to practice the code to traverse to find the size. What else? We don't want to create a lot of redundant code because many methods are going to require similar traversals, right? You're going to be walking down the list to find things in several of the algorithms. So you want to keep in mind, I don't want to write the same code multiple times, right? So think about that, and also keep traversals to a minimum. You don't want to have helper methods and methods built on other methods that become very inefficient because each one traverses the list to get to where it needs to go. So you want to keep that in mind too. Now those two things may seem like they are going to fight with each other, to be conflicting, but really they're not. You can certainly do that, and remember, helper methods, just like all methods, just like we've used in other kinds of hazard relationships, a helper method doesn't have to return an index, it doesn't have to return some other kind of data, it can return a reference to a node. And if it does that, then the next thing that builds on that can just take that reference and start there. So we want to think about that and be efficient in our traversal, because now we know linked lists are not going to let you have random access, right? You can't just say I want the fifth thing and automatically it goes in memory like an array. So we want to be a little more thoughtful here and be efficient in our algorithms. So let's look at some of those algorithms and what the typical kinds of operations and how we write those in code. The first thing is, what if we want to add something at the front? Well, the first thing that we're going to do is we're going to create a node, right? If the client code asks us to add particular data, like they say, hey, I want to add a string, maybe this is a linked list that works with strings. If they pass us, hey, I want you to add Dana, and I want you to add a Dana at the front, first thing we have to do is create the node, right? So we have a node data type. We set its data. It's not pointing to anything, right? So this is a little symbol that I'm just saying, hey, this is null. I could put null here. This little arrow pointing down just means null in this particular diagram. So the first thing we have to do is we have to make a node, right? Because you can't insert a string into this list. You have to insert a node into the list. Now, the other thing to think about is the thing that we can't do is to simply point this pointer that's now pointing here at this node. We can't just direct that to point here. What would happen if we did, right? If we just remap this pointer to go from here to here, what would happen to Chris and everybody past Chris in the list? They would all be garbage collected, and all we'd have in our list is one node. So we definitely can't do that. So part of the fun here, and fun in quotes, part of the mental exercise here is you got to figure out how to do this thing in the right order so that you don't lose all those other nodes. So what do we need to do? Well, there's a process here. First, we need to repoint this thing to here, right? We need to take the new node's pointer, the next pointer in the new node, and map that to be pointing at Chris. Well, how do we know where that was? How do we know how to point this to this? Well, front is pointing at this. We need to point this at the thing that front was pointing to. Does that make sense? Point new node dot next to the thing that front points to. Remember that when you're using references, think of equals as points to the same thing as, right? This is a reference, this is a reference. So think of equals as being, the equal sign as being points to the same thing. So point new node.next to the same thing that front is pointing at, right? So that takes care of this first step, which is to do this. We have to go in this order. What's the next step that we have to do? Well, now that this has a secure hold on this, right? This has now got this safe. Now we want to point front at this, right? Because now this is the new front of the list, right? We're adding to the front. So front needs to point to there. So how do we do that? Well, we add another line of code that says front points to the same thing that new node points to. Front points to new node, right? So that does the second thing. Now, typically, when we're in this method, we've created the new node, but that's in a method, right? So what happens when the method ends, a new node goes out of scope? Well, it just, that reference leaves, right? That reference is gone, but we don't care because we're going to have this global reference called front, and now it safely points at this. So if new node is X'd out, we don't care, right? This is all still safe, and now we have, in fact, added Dana to the very front of the list. Yay. Right? So we just have to do things in the right order. This has to point to this has to point to this, and then if we have some variable that goes out of scope, oh well, we don't care, that's not important. Hopefully that makes sense. So there's the code, right? New node.next equals front, front equals new node, and then new node just goes out of scope. We don't need to destroy it, it'll go out of scope when we hit the end of the method and it's gone. Hopefully that makes sense. Pause, look at that. Go back a little bit if you need to rewind in your brain and see that happen again, because that's a really important step. What happens if we need to count the nodes? How do we go through all of them? Well, we got to start and have something that moves along, right? We've got to have some little reference that kind of goes node to node to node. Very typically we call that current. We set up a node and we're going to point at this first node, right? We're going to use current as a pointer to point to the same thing front points to, which is going to be here. And then we simply have to follow .next and .next, and we keep doing that until we get to a null. Okay, so what does that code look like? Well, we have a node count variable set to 0. We start a thing called current, a variable called current, and it is a student node reference, right? If this is a student node data type, it's a reference just like front is, and it points to this thing first. And then we can write a loop that says while current is not null, right? So right now current is not null, and then we simply move .next, so we say current equals current.next. This is a funny line of code. You're going to see it a lot, so stop and ponder it. If we're here, this is current. When we say current dot next, we now follow the same thing. So follow that next pointer to here, right? So current equals current.next means follow the next pointer in this node and be on the last node, and then remember that current is now here. Right, so that updates current to be on the next node. And we keep doing that and adding 1, incrementing the count until we get all the way to here. And in fact, this code, if you'll think about it, actually says current equals, like if current is here, it goes current equals current.next. So it actually has current pointing to null, but as long as it checks here to make sure that current is not null, then that's fine. Notice it never tries to act on that, right? It's okay that current becomes null. We just got to make sure that current doesn't try to then say dot something, right? The dot would be the killer here if we tried to use that when current is pointing to null, as it would be at the end here. So in a debugger, it might be really good for you to go and stop and watch the value of current and convince yourself it's okay for current to be null. There are algorithms where it's not, because you're going to then try to dereference, and that's a problem. Right? So for size, we could do this. Now, of course, we should probably keep a separate count, right? It's just easier. Why would I traverse every time I need to count? Okay, and this is just reminding us that the dereferencing would be a problem. So it's okay for current to become null, but it better not try to act on that by using it to do dot something. Okay, now there's going to be some, we're not going to walk through like fancy code on all these, but let's just talk about the idea. What if you needed to go to the end, right? What if you needed an node to be added to the end? Of course, you got to create the node, and then you have to be there, but be where, right? Where do you need to be? Well, I need to be here. I need to make sure current is here, right? And then I can simply set current.next to point to the new node that I created, right? So the key bit of code is current.next equals new node. So that should be fairly straightforward if you've paid attention to what was going on here. So really I just need to map that pointer, map that reference to something new. Okay. What about removing? What if we want to get rid of, in this case, Pat, right? If I want to get rid of Pat, what do I have to do? Well, again, I have to traverse. Now, this one is tricky, right? And in class, we'll talk about some different nuances here of what you have to do. But the most important thing is you've got to end up with some pointer here, not here. If you've already moved from current to here, it's too late because what you need to work on is actually this next reference, not this one. You don't care about this node at all. So if you've traversed here, you've gone too far. And there's several approaches to dealing with that. There's a thing called an inchworm where you move along and have a trailing pointer behind you, where if current gets here, then you have another pointer that was lagging behind. So you can have a lag pointer. You can also do what I call a long arm approach, where you just need to make sure that current lands here and you're looking to the next spot to find Pat, right? So one way or another, you've got to have a reference that ends up here on the node before you want to delete. And then I think you can see it's really not going to be that hard because all I need to do is map this to point to this. If I take current.next and I point it to this, then I just let Pat get garbage collected and now I have the right node as my next. So what does that look like? Current.next equals what? How do I then get here if I don't have this? Current.next equals current.next.next, right? So the code looks confusing. Current.next equals current.next.next. Set this node's next pointer to point to the same thing that the following node's next pointer points at. Current.next equals current.next.next. Again, looks funny when you see this first. Stop and watch it again if you need to convince yourself that that is actually the thing that you want to do because you're remapping this. This is what you're trying to accomplish. And you don't need a pointer to this to do that, right? Because you can navigate through the next pointer here to get to here. Right, so this is current.next, this is current.next.next. You're mapping this to this, which you should see in this code right here. Does that make sense? Again, pause, go back if you need a moment. These things you need to code for yourself, right? You've got to make up a simple list, a linked list for yourself in order to practice these, because just seeing it in code here is not going to help. You've got to draw it out on paper. You've got to write the code. You've got to test it to make sure that you're doing everything correctly. It's the only good way to learn. You're cheating yourself if you don't do that. Okay, a couple more operations real quickly. How about add in order? If I want to add this student and I want the student last name of Carrillo to go between Barajas and Chavez, let's say that I'm trying to keep these sorted by last name, I think that by now hopefully you've got the idea of what you need to do. You have a thing called new node that's going to point to this. You need to get current pointing to here, right? What do you have to do next then? Well, you have this. You can't point this to this or you're going to lose Chavez. So what I need to do first is take new node.next and point to current.next. And then I need to take current.next and point to new node. Right, so very similar to what we did with adding at the front. You've just got to get those things clearly and carefully mapped in the right order. Okay, so these things start to make sense. They start to feel more familiar as you start coding them. So that one's another good one to code. Find where you want to be, again, you've got to end up here. If you go to Chavez and you decide, oops, Carrillo belonged before, you got to get back, right? You're too far. So again, you've got to use either an inchworm approach to make sure you stop here, or stop here and have a lagging pointer, trailing pointer, or you've got to use what I call the long arm approach, which says, hey, I'm looking here to see if the next thing is too big, and if it is, then I know to stop. But one way or another, you've got to stop here, so you can say new node.next equals current.next, and then current.next equals new node, right? So all that code, practice it. Now, how about an easy one? What if I want to clear the list? Well, that's super easy. Front equals null, right? That's it. Because you make front null, everything else goes away. The garbage collector does its thing, and it's a go after that. Again, these things become easier and easier as you think about them. What if you want to combine these two lists? You have this list and you want to add this one onto it. Well, that's actually very easy to do, right? All you have to do is point this reference that's null right now to this student, and everything comes together, right? Everything comes together. So that could not be easier. So a lot of these operations make a great deal of sense as long as you understand the idea of navigating. Where do I have to end up, right? Where do I want to have my current pointer so that I can make sure that it's in the right spot to act? And then the reference stuff will become normal and easy to you, but you do have to work with it a bit. Okay. In terms of helper methods, what's interesting with those? Well, you might want to have things like this where you can give it a value, you can give it some data, and have it tell you where that is in the list. You also probably want to have a thing called something like node_at, where you give it an index and it actually gives you a reference back so that you don't have to traverse again. Also, sometimes you want to have several different constructors because sometimes you know the data ahead of time. Sometimes you actually know the new pointer ahead of time, which means you can really shortcut the operations. And sometimes you don't know anything yet. So having several different helper methods, different constructors, can make life a lot easier because you can do some of the pointing at the same time. Okay. Now we have another couple concepts to talk about. We're going to want to talk about dummy nodes and how that affects some of the coding here. So we're going to talk about that, but I think I will break the video here because it is getting a little long. We don't really have that much more to go, but I want to make sure we don't have to rush. So thanks for watching this video. Come back. We'll talk about a couple of implementation details of how linked lists are often put together and how dummy nodes can help make your coding life easier. So thanks for watching this one. Come back. We'll finish up with the next one. I don't think it'll be a long one. Thanks.